My name is Marko Tisler. I work for Arrowhive Networks, and today I'd like to talk about indoor location detection using Wi-Fi. More particularly about the accuracy, the expectations, and what actually gets delivered. Because there's a lot of misconceptions about the accuracy, both in time and in terms of location. So what I'm talking about is the customer who wants to deploy Wi-Fi location detection expects GPS-like experience without, a scale of a city or a country, but a scale of a floor or maybe a large hall. And so basically they are expecting, hey, you're here and you're here now. So what's actually happening is we're saying you're sort of somewhere here in the building. That's the actual experience. So you're sort of somewhere here in the room, and we're not going to put our hand in the fire and say, hey, we guarantee you that you're actually here, right? So that's how Wi-Fi location works. With a certain accuracy, with a certain probability, we're saying you're probably here. Yeah. So once you start this honest discussion with the customer, it gets tricky. So the way it works is you go to your prospect, to your customer. Let's say that's a retailer. You are there to present your location analytics solution. And they ask you, okay, so if I understand correctly, this is what you can do. If my customer stands in front of a shelf with coffee, you'll be able to tell me whether they're looking at coffee or chocolate on this side. And you say, no, that's not what we do. You explain it cannot detect which way the customer is facing, etc. And they say, okay, that's fine. I know I was too optimistic. So, but what you can do is, here's one shelf, there's another shelf behind it. So you'll be able to tell me whether the customer is looking at the coffee or at milk at the other shelf behind it. And that's probably like 2 meters apart or a meter apart. And you say, not quite. Because, there's a tricky thing about Wi-Fi. It's actually not that accurate. And then you get to a point where the customer or the prospect says, okay, so what you can do? Again, you say, we can tell you that the customers are mostly sort of here at this shelf, not at the other shelf. And then it gets hard to sell. The next question you have is, okay, so let's say you sort of positioned the accuracy bit. Then you start talking to the developers. And they say, okay, so when is this information available? When can I actually see where a certain device or a certain user is? Is it real time? Is it not real time? Is it sort of real time? And your answer is going to be depends. It depends how accurate you want your positions to be. It depends whether your client is associated or not. And because most developers don't have any Wi-Fi concepts covered, they say, what? And then you start saying, okay, so here's the thing. If your client is not associated, we're talking about 30 to 60, maybe 2 minutes delay. So 30 to 60 seconds or 2 minutes delay before you get your information. Because here's the thing, the client has to probe, and we have to catch that probe in order to actually do any triangulation. Okay, then the developer says, so it's not real time. Yes, well, it's sort of real time. Yeah? And you get into this awkward conversation again. Then you get into the conversation, okay, how about history? Well, again, it depends, right? Are you storing the history? Are you processing the history? So, and from the perspective of a developer, what I need to do, one API call, I need my location for client X, and I need it now. Okay, so again, is this misconception and this expectation versus reality paradox. So when you come in, this is what your customer thinks you're doing. You are the expert for location analytics, you are very accurate, everything is really straight to the point, so like architecture. What you're actually doing is this. You're navigating a stormy sea trying to find that client as soon as possible. RF is messy. We all know Wi-Fi is messy as well. And here's going back to something that Keith said, is it's hard to make Wi-Fi work really good. It's even harder to do Wi-Fi location really good. It's very easy to do Wi-Fi location very bad. Yeah? So, for example, this is from personal experience. I had a project where it was in an emergency room of the hospital, and they said, okay, so we have this operating rooms, and we want to know exactly in real time when somebody is in a certain room. And the rooms are basically like 5 meters across, one next to each other. Well, you can't do that with Wi-Fi, can you? So we had to include some other technologies to be able to do that. But their expectations was, hey, Wi-Fi can do that. No, sir. And especially in an ER, people die there. So you don't really want to mess with, hey, we're sort of doing this right. No, it has to be, it's either right or it's wrong. The reason behind this is we are still relying on RSS based methods. So we've seen something similar to this graph yesterday. And this is the relationship between the RSSI in dBm versus distance in meters. And this is a theoretical model. It only works in a desert free of any noise and only in perfect conditions. And you can actually produce this relationship for any frequency you want. And there's the equation. So we are able to calculate the distance from the transmitter, so between the transmitter and the receiver, based on that equation, and we are able to evaluate the distance. If we do that for at least 3 devices, we get the possibility of doing triangulation. So we're able to say, okay, so if I have 3 distances, I'll be able to get x and y only in 2 dimensions, x and y for that specific device. Cool. And it turns out you have to solve this system of equations, which is pretty simple once you have the measurements. And this is what we call triliteration. Problem number 1. The further away you get from an AP, and this is what we saw yesterday, I think Carl presented this. The further away you go from the AP, the same drop in RSSI means a larger change in distance. So when your RSSI changes by 3 dB here, that means, let's say, I don't know, 6 meters. When it changes by 3 dB here, that is 10 or 20 meters, which means your error grows the further away you go from the AP. Which means this sort of procedure works sort of okay if you're near all the APs, and it starts degrading as soon as you move away. It's actually even worse than that. So we all know that RSSI in real life doesn't behave in a linear fashion. It jumps around like crazy. So instead of having this smooth hockey stick, we have this jagged, weird, not even approximation. We have this quasi-random behavior of RSSI. So in reality, what happens is, so at first it behaves okay for a couple of meters. Then it starts jumping up sharply, presenting you to be closer than you actually are. Then it drops sharply, making it look like you're further away than you actually are. And something interesting happens once you get really far away. So let's say 15, 20 meters away. RSSI sometimes jumps up, making you again appear close to the AP. Now try to explain that to your customers. So what happens in reality is, the theory said you're positioned somewhere around here, so behind this wall in that office, according to that RSSI model, because of several factors. First of all, absorption of walls and other materials in the room. The RSSI is lower than according to that model. So in reality, you're actually closer to the AP. How do you work with that? And one of my experiences was I was helping a startup that was sort of pitching inside retail analytics to customers, make sense out of all of this messy stuff. The startup failed, so I'm here and I'm able to talk about it. First thing that we can do is we can do RF fingerprinting. RF fingerprinting means, okay, so let's throw the theoretical model away because it's obviously not good, and let's try to make real measurements of actual environment. So we go around the floor plan, taking measurements of RSSI from different devices, and put that in some sort of database. And then once we take actual measurements from the environment, we compare that to the measurements we've made. And it's called RF fingerprinting. It takes a lot of time. One of my colleagues called this the Wi-Fi dance, because what you need to do is you need to take one of your clients, you walk around, and take RSSI measurements. Now the problem is different clients will make different measurements. You are doing the measurements with your MacBook, but the people coming in to the store are actually using Android smartphones, HTC, Samsung, whatever. But you are sort of accounting for non-line of sight situations, material absorption, etc. It does sort of improve location detection. However, there is a lot of effort involved, especially if this is a large venue. And even if you do this, we all know that RF is and will always remain a dynamic environment. So even if you go through all this effort, two things are going to change. So one thing is, sooner or later somebody's going to change the layout. Or an AP is going to stop working. Or it's just the position of the device. So when you did the measurements, you were holding the device horizontally. When somebody's using the Wi-Fi, he's using the device like this. And the RSSI just goes like this. So this doesn't really help you that much. And it comes at the cost of doing a lot of work. Okay, so we live in 21st century. We have this cool thing called data science. Let's get some big data scientists or data engineers, and let's take this messy data and try to filter it out. See if that will give us a better accuracy. So we take this large amount of messy data, throw away the low RSSI measurements because we saw they don't really correspond to our model that well. And then maybe we take into account the fourth or the fifth strongest signal, do some sort of multi-iteration. But you soon find out this is very costly in terms of resources. And it's still an assumption. So you do a lot of post-processing. You pay the price in terms of CPU, memory, probably data storage as well. Because this sort of things have thousands and thousands of clients, right? This is not a deployment with 50 clients. For example, if you look at a deployment like Dubai Mall or something like that, this is thousands and thousands of clients all the time. You're taking measurements all the time, and you're putting that, if you're smart, in a non-SQL database. If you're not so smart, you're putting it in a SQL database and see what happens 1 month later. And then you do post-processing. Yeah, and now we come back to the question, when is that data available? Well, once we post-process it, when's that going to be? In an hour? 2 hours? Okay, so the real-time stuff just goes down. So it's really problematic. There are other things we can do. We can cheat. We can say, okay, we know enough about the actual environment so that we are pretty sure that some locations are invalid for clients. So we can say, okay, if a location is invalid, snap it to the nearest valid location. Now the problem is you started with an error. how do you know you're snapping the client to the correct location? Maybe you're just introducing more error. Or a popular method seems to be snap to line. You draw lines across your floor plan, and you try to snap a client to that path. Now, what if the client is outside your location and they're being snapped to your path, contributing to the statistics that you want or your customer wants and making it false again? So basically what you're doing, any sort of alteration to that data just skews it further. There's just more and more fallacy in that data, making it more and more unusable. Obviously, it looks good to the customer, right? So suddenly you have these nice lines. The customer says, okay, now I know where my clients are moving. I know where my customers are moving. I'm happy because this is what you wanted to sell the first time. But if you actually went in and check every single data set that you have, you see that a lot of it is clients coming out from the outside of the environment, just invalid measurements, probably even clients that were snapped from a valid, invalid location to a path, or things like that. So, okay, this doesn't work. So there's another approach. Instead of counting on X and Y coordinates, let's try to do something like a path analysis. So let's forget about X and Y. Let's just try to guess, on average, where do people move, or where well do people dwell? So on average, that may be correct, it may be not correct. It's really hard to prove whether, whether it's really 90% of the people that are going across that path, or maybe there's something we're not doing correctly. And it's hard to evaluate those methods. You don't have access to the data set, and it's troublesome to do the actual measurements and compare them to what the application is giving you. So the problem now becomes, what is the credibility of this stuff? How can I trust it? Because the proposition is, hey, Mr. Customer, you have some business processes, and we can give you insight to help you with those business processes. And now you're trying to change your business processes to the data that may or may not be reliable. Oops. So RSS has some strengths. The data is available right now. Any Wi-Fi network can provide that data to you. It's very opportunistic. It's very cheap to start with. It's expensive once you scale. Remember the SQL database stuff. And it supports unassociated clients because they are, as soon as the Wi-Fi is turned on, they're probing, and you are able to evaluate their position. Accuracy, somewhere between 5 to 10 meters. You normally need to do some sort of post-processing, which makes it costly to scale, and it's even more problematic in terms of accuracy when your clients are on the move, when they're moving around. Then your accuracy just goes down. So, is there any other way? There are some alternatives. We do know about time-based methods, and we have two different approaches here. One is, let's measure round-trip time for a frame. Because if we know the distance between different nodes, we obviously know the speed at which the signal moves, we are able to calculate the distance. Or, let's take several measurements and compare time of, let's say, reception of a frame between different nodes. And then we can say, okay, from the station to this node, it took this much time, and to the other two, it took this much time, which means we can calculate the distance and do our true iteration again. So the first method is called round-trip time, and you have two choices here. You can measure the amount of time, which is known, for a frame to be transmitted to the client, so from the AP to the client and until the time you receive an acknowledgement. These are known values. And based on that, you can estimate, okay, this is the distance between the client and the AP. Or you could use RTS, CTS, if you're using that. So because this is a known time, and because the signal travels at a known speed, you can calculate the distance. Cool. The problem is the client needs to be connected. So forget about using this for the unassociated clients. Now, back to the question, how do we trust these methods? It also goes back to something that's been mentioned here today and yesterday. What are the values whether something is good or bad in Wi-Fi? Or what are the how do we say whether something is good and bad in location detection? Well, there's something called what we call a confidence factor, and it's not often given out. If you look at the probability distribution of your errors, or what's called cumulative distribution factor, CDF, and you compare RSSI to round-trip time. On the bottom, you have position error, and on the y-axis, you have the probability that the error is lower than that. So if we check RSSI, we have somewhere like, let's say, 90% probability that the error is lower than 8 or 9 meters. That's RSSI. Round-trip time, less than 90% of the time, the error is going to be less than 2 meters. So, okay, this is better, that's better. And this is actually something that you can use to weigh or evaluate the methods that you're using, right? Nobody's giving this out. Nobody's saying, hey, we're doing location accuracy with this sort of confidence factor. How is it obtained? Well, through experimentation or simulation. You can't really say for sure this is the accuracy. We're saying we're 80% sure that the accuracy is going to stay within these limits. Whoops. The other method, which is already known from outdoor location positioning, time difference of arrival. Basically, you work under the assumption that there's going to be several nodes that will be detecting the frame being sent out from the client to the AP. Because Wi-Fi is a polite protocol. When somebody talks, everybody else listens. So when you listen, you have time to do stuff. So you listen for when you receive a frame, and you compare those timestamps to evaluate how long did the frame require to travel over the air, and again, you can get the distance. So TDoA, what does it give us? In terms of our confidence factor, and this is an actual experiment done at a university, we are between 1 and 2 meters of accuracy. The problem, there's several problems. First of all, we need line of sight from at least 3 stations. All the stations need to listen on the same channel. How often do you get that in your high-density Wi-Fi? Requires several samples, but that can be achieved. More importantly, the clock needs to be synchronized. So the only way that these measurements make any sense if you have synchronized clock to something called a global clock. And we're not talking about NTP here, we're talking about microseconds. So NTP is not going to do this for you. You need a specific clock, a dedicated equipment that's going to provide the clocking for you. Now there's good news to this. You can do that without the clock. So it's been proved, and I'm not going into the details, but it's been proved that there exists an asynchronous method to doing this. If you are able to have 20 megahertz or larger clock frequency on your receiver. So if you're able to do 20 megahertz clock ticks, you are able to derive this information, the same information, without having a synchronized clock. Which is good, because now you can use cheap equipment to do this. The problem still remains. All the stations needs to be on the same channel. You need several sources, several samples of data, and more importantly, you need line of sight. At least 3 stations need to see this in line of sight, which in some cases, so if you imagine a warehouse or if you imagine a store with shelves, that can actually be achievable. So we're getting closer. So in terms of weaknesses and strengths, round-trip time, it's pretty accurate in terms of distance measurement, especially when you compare it to RSSI. The problem is, it only works for connected clients. So yes, we often need to combine it with something else. TDoA, again, pretty accurate, can work for both connected and unassociated clients, and it's been also proven that it works pretty well for the clients that are on the move. And best of all, it's pretty real time. You don't have to do any special post-processing and things like that. It can give you that data pretty quickly. So in terms of resources that you're using, this is pretty efficient, especially if you go for an asynchronous mode. Now there are some problems. The APs need to be on the same channel, and you need to have several frame samples which may not be available when your client is probing, right? It depends how many frames it's sending out. The last method, angle of arrival. The reason why there is a fighter jet over here is I've been told that this same technology is used in fighter planes. Basically, you have an antenna array. It doesn't have to be a large array. It could be 4 elements. What you're able to do is, based on the phase, you're able to say, hey, the signal came from this direction. So based on your antenna position, you can say, okay, the client is over there, and based on the either signal strength or round trip time or whatever, you can say, okay, that's the distance. So you're getting more accurate with this. The problem is, there's free versions of this implementation. One is cheap. You just need several elements, several antenna elements, need to derive the phase, do a cross-correlation of the signal, and then you'll be able to discern at what angle did the signal come from. The problem is this method, the cheap method, is very, very, it doesn't tolerate noise very well. It's sensitive to signal-to-noise ratio. So as long as your signal-to-noise ratio is above 15 or maybe even more, 15 dB, it's going to work. As soon as it drops below that, forget about it. So how do you control that? There are 2 more expensive methods, but then you're spending money on your hardware. So angle of arrival, accurate positioning, can work with a single AP, by the way, which is pretty cool. It can cost a lot, especially if you want to go for the signal-to-noise ratio or noise-resistant method. Or there's something else. So you either invest in hardware or tune the environment, which means position your APs, and then you have to do some measurements to measure the signal response, and then you're able to do the cross-correlation to get the angle of the signal, which is time-consuming, and, well, nobody wants to do it. There's more. There have been several hybrid methods that have been implemented and have been proven to work pretty well. One is, okay, so we have several sources of truth where the client is. Let's say we have the RSS, the received signal strength. We have the round trip time. So let's combine those 2 sources of truth to use RSS worst case, so when the clients are unassociated, and then combine it with RTT once the client is actually connected. This gives us, so if the client is connected, this gives us sub 2 meter accuracy. If the client is unassociated, this gives us 5 to 10 meter accuracy, which is still better than missing out on the client. Or maybe pair RSS with one of the TDoA types. So if enough samples are gathered, we're confident that our TDoA is going to work well. So use TDoA. If we don't have enough samples, use RSS. Or the third example, we can actually use client-side information, especially if that client is on the move. So most of smartphones today have accelerometers. And if you have an accelerometer, you know how your device is oriented, what the position of it is, and where you're moving, and how fast you're moving. If you use that data from the device to augment what you're measuring, you can actually get pretty decent location. The problem is you need an app on your phone. Who likes apps on their phones? What's the retention rate of an app on your phone? Supposedly up to 3 weeks. So and let's say there are several retailers using this, are you going to really install apps for all the retailers you're visiting? I certainly wouldn't. But yes, it's been proven that this can work pretty well. Now, once you've figured out how to get that data, and once you've convinced your customer, hey, this is the confidence factor, I am 90% sure I'm giving you the information that is within 2 meters, 90% of the time. Now how to get the data out? Well, you need an API for that. And usually you don't or can't do all the post-processing on your own, because when you do post-processing on your own, maybe you're discarding information that the customer wants. Maybe you are interpreting that information differently than it should be interpreted in a specific environment. So you don't know the business processes, and you don't know what the data is actually going to be used for. Then there's the question, how real is real time? When is that data available? So if I request it now, will I get data from 1 second ago, 1 hour ago, 1 week ago? What am I getting? Am I getting the confidence factor? Are you telling me how sure you are this data is actually correct? What about historical data? So how long do you keep it? Is it available? And especially in Europe, what are the privacy concerns of storing and exchanging that data? So this is sort of customer information, right? And I was consulting one of the legislatory bodies in the EU, and they said that your phone's MAC address is actually personal information. They treat it as personal information. So like your passport, personal information. Your phone MAC address, personal information. So, okay, what do we do about it? Do we encrypt? If we encrypt, what does that mean for the data interpretation? Do we do a one-way hash? What do we do? What do we have to do? And most importantly, how does it all scale? So I've been through several implementations of this, and trust me, the only way this scales is through the cloud. It just doesn't scale any other way. And when I say scale, I mean thousands and thousands of clients, hundreds or thousands of APs. That's what you want. And don't use traditional relational databases. You're going to get burned. It's going to burn bad, because they are not equipped to handle this sort of this amount of data getting in, especially when you do long-term trend analysis and things like that. Okay, so that's pretty much it from me. Thanks for your attention. Any questions?
Question? Oh, all the way in the back. You see, then you hand it to Scott when you're done.
First of all, thank you so much. Very, very good and informative presentation. And you know, being in the RTLS industry for 15 years myself as well, you've clearly done your homework. So, you know, put a lot of thought on the drawbacks of the systems and the benefits. And I agreed with nearly all of them, except maybe the RSSI accuracy can be tuned to be slightly higher than 5 meters to my experience. And the second thing was that clients on the move, at least with the system we used to have, we sold our RTLS business, but the system we used to have, it was actually more accurate when the clients were in the move, because we were frequently getting polls from either from the infrastructure or the client, RSI-wise. So you know, when the client was moving, the historical trends that we followed made it actually much more accurate than when it was stationary and it started to hover, because it started to get more and more unsure of where it is. Just an observation. Last thing, if I get an okay from my management, would you be willing to come and talk about these things to our webinar as well?
I'm sure I could. Have to talk with my manager, but I'm sure I could.
That would be nice. Thank you.
So one thing about the RSSI bit, 5 meter accuracy is on average across the different verticals. So you don't necessarily, different verticals, different environments means different things. And with the thing what you're saying about the moving client is, it depends on, so if you're doing it like this, it works. But what people are actually doing is going like this, doing the Wi-Fi dance, and their RSSI just goes. So I've been doing this in a hospital, right? And I assumed it's going to be like what you said. So when you have an RF tag, it works like you said. When you have a smartphone, a device that user has, they push it against their heads, they sit on it, whatever. It just dances around. Yeah, that's why it works pretty well in hospital basements.
I get the feeling that RTLS maybe isn't dying technology, but particularly with the analytics, you've got BLE and other technologies that are more accurate. Is RTLS in traditional healthcare was obviously the main market? Is that still, are customers still? Is that still being deployed? Are all the vendors now looking at these more accurate technologies?
We're looking at hybrids, to be honest. So that's a very good observation. The RTLS, the traditional RTLS, it's still there for healthcare. But for other verticals like retail, logistics, and things like that, it actually turns out, so BLE is a good example. And by the way, these techniques don't apply to Wi-Fi radios only. They can be used across different frequencies, across different radios. It's not something that's Wi-Fi specific. And ideally, so I think what the future is using several radio technologies, like some information from Wi-Fi, complement that with BLE, you have several sources of truth, and then you try to approximate what the truth actually is. So I think that is the future. And maybe Google or Apple will expose some sort of API to their accelerometer, and you can tap into that information as well. But we'll see where that goes. Yeah, angle of arrival. So, from what I know, so Cisco has this Halo antenna. The question is, how does that correlate to what was presented? It's angle of arrival, several antenna elements, I think 32 or something like that. So from my experience, you don't actually need that many. But yeah, it's on steroids. So it basically makes you invest in more hardware. You're investing in more hardware to get more accuracy, basically. That's the idea. That's the big problem, yeah. So most retailers, they don't want to force you to go to a captive web portal, register, or they don't want you to use an app, because that proved to be inefficient. The whole Wi-Fi monetization scheme that just fell apart. 5 years ago, we started talking about it, and then they didn't stick. So now they say, okay, we want passive detection, right? And passive detection has some limitations with all these methods.